In this video, we'll be talking about pressure's effect on states of matter. And so in figure 1, I've drawn a PT diagram. That's pressure on the y-axis, temperature on the x-axis. And for a given temperature, so say we're at this temperature and a given pressure, all you have to do is find out where you are on the graph, and it tells you what state of matter you'll be in. And you'll see that this whole section over here is solid, anything over here is liquid, and anything over here is gas. And that temperature and pressure affect what state of matter you're in. And temperature we already kind of know, right? And if we had a solid here, and I increase the temperature, it would be a liquid, and that makes sense. Or if I had a liquid here, and I increase the temperature, it could become a gas. And at low pressures, I could have a solid become a gas, right? And that would be sublimation, boiling, and melting, respectively. And it's important to realize that these lines that separate between the solids and the liquids and the liquids and the gases and the solids and the gases are all special, right? These lines actually show you the temperature, the specific temperature at which you can have a solid and a liquid in equilibrium, right? So that means at 0 degrees Celsius, I could have solid ice and liquid water, and they could just stay there indefinitely. Now, if I were a little bit warmer than that, at 1 degree Celsius, eventually all that ice would melt, and I'd be all liquid. And if it was at negative 1 degree Celsius, eventually all of that liquid would freeze, and I'd be all ice, I would be all solid. But if you're right on that line, you're in between solid and liquid, right? And that kind of makes sense graphically here, because if you're right here, in between solid and liquid on that line, you could be a mix of solid and liquid. And if you're a little bit to the right, you're a liquid. If you're a little bit to the left, you're a solid. And so the line between solid and liquid represents the melting point, right? What that temperature is. And the liquid and gas would be the boiling point, and the solid and the gas would be the sublimation point. You notice that there's one special place here, the triple point, and that's a specific temperature and pressure at which the solid, liquid, and gas phases of the substance can all exist together in equilibrium, right? They can all stay solid. There can be solid, liquid, and gas indefinitely. So the really interesting thing that this diagram tells us is that all of this depends on pressure. So I could also go from a liquid to a gas by decreasing the pressure, or vice versa, right? I could go from gas to liquid by increasing the pressure, or from liquid to solid, right, by increasing the pressure, or solid to liquid by decreasing the pressure. I could do the same between solid and gas for sublimation. And this is a little less intuitive than our temperature stuff because we see the effects of temperature in our everyday lives. So I want to just remind you that in figure 2, increasing pressure, one way we can do that is decreasing the volume, right? And the effect is that it kind of squishes the molecules together. And decreasing the volume increases the frequency of the collisions of the molecules with the wall, right? Because there's less distance between the top and the bottom. But also it increases the pressure because there's kind of less area for that force to be spread out over. So I showed you increasing pressure by decreasing volume, and I showed you going from gas to liquid to solid. And we could see that on this graph, right? If I went from here, gas, liquid, solid, all by just increasing pressure, right? You see that this is all happening at this temperature, and the only thing I'm doing is increasing the pressure. And that's what I've done in figure 2. You see that as I increase the pressure, I'm squishing them together. I'm making them closer together. The molecules are now closer together. And to remind you in figure 3, right, the distance that the molecules are apart is a big part of their potential energy, which is a big part of their states of matter. So if they're really far apart, they're gas because they're so far away that the attractive and repulsive forces don't really apply, right? It's too far away. Now if I make them closer together, I can get them to become a liquid. So where they're kind of attracted to each other and there's this negative potential energy, but not as much as a solid, which is kind of at that maximum where they're in their crystalline structure. So you see that as I increase the pressure, I'm really decreasing that distance between them, which will change their state of matter. The last point I want to make is that as we increase the pressure on this graph, we see that the temperature at which something will melt or boil increases, right? So if I'm at this pressure, if I go across, I could say, okay, then things will melt at this temperature. And if I increase that pressure to here, it's more like here. And just a way to think about that is the pressure is kind of how much is like kind of forcing you down. So I drew in figure 4 a solid and gas pushing it down. And the more force pushing you down, the harder it is to escape.